Much better. Okay. So warm-up question number one. It says to use synthetic division. So synthetic division, if you remember back to unit 3, which would have been a few weeks ago at this point, whenever we divide by synthetic division, it has to be divided, first of all, by a linear binomial, and the coefficient of that linear binomial has to be 1 in order for synthetic division to work. So this is a linear binomial that is being divided by, and the number next to x is 1. So we're good to use synthetic division. The number that goes in, this is where we had the little box up in the left-hand corner, and there's a number that went in that box right there. And we got that number by looking at this linear binomial. Does anybody remember what value ends up in this box? Positive 1 or negative 1? Negative 1. Okay, how come? So it is negative 1. Why would it be negative 1 instead of positive 1? Yeah, it's whatever makes the set of parentheses equal to 0 here, which in this case is negative 1. All right. Then we list off all of the coefficients from our first polynomial over here. Just the coefficients. No x's, no exponents, no nothing like that. So start with 2, and then 7, and then 4, negative 1, 6, and 6. All of the coefficients. Now, every single factor of x needs to be accounted for as well, which it is, because we got a 5, a 4, 3, 2, 1, and then no variable at all. But if there was anything missing, we'd have to use the placeholder 0 in order to fill in for it, if that was the case, which it isn't on this one. All right, then we've got our line here for the answers that we're going to end up with. And then we're going to have another little box down to the bottom right for if we have a remainder, that's where our remainder is going to end up down there. All right. Does anybody remember the first thing we do in this process? Zane. Bring the 2 down. Yep. The first coefficient drops down into our answer right there. And these values are part of our answer, part of our quotient. And then we go through a very repetitive process. Does anybody remember how this process starts? Yeah, Zane. Yeah. Multiply the number we just brought down by the number in the box. And then we write it underneath the next coefficient. So we're going to write it under the 7. So we're going to get negative 2 right underneath there because negative 2 times, or 2 times negative 1 is negative 2. And then what do we do with the 7 and negative 2? Add them. All right. What's 7 plus negative 2? 5. And then that process repeats. So then 5 times negative 1 is negative 5. Add them together. 4 plus negative 5 is negative 1. Repeat the process. Negative 1 times negative 1 is positive 1. Negative 1 plus 1 is 0. Repeat the process. 0 times negative 1 is 0. 6 plus 0 is 6. Repeat the process. 6 times negative 1 is negative 6. Negative 6 plus 6 is 0. So there is no remainder. So this would be our remainder if there was one, but it's 0. This 6 is our constant term. This is our linear term, x. This is our quadratic coefficient. This is our cubic coefficient, 5. And then our quartic coefficient of 2. So our answer for this, actually, we did need all those spaces, is going to be 2x to the power of 4 plus 5x cubed minus x squared plus 6. Because there's no linear term, so we don't need to write that in our answer. If it's 0, you can just leave it out. And then the remainder was 0 as well. So if you take 2x to the 5th plus 7x to the 4th plus 4x cubed minus x squared plus 6x plus 6, and you divide it by x plus 1, you end up with 2x to the power of 4 plus 5x cubed minus x squared plus 6. That will be our answer. All right. Let's go and do the next one then. So we're going to have our box. Upper left. What number goes in this one? 2. Yeah. Because this time it was an x minus 2. So the opposite of the value that's in there, or the number that makes this set parentheses equal to 0, would be positive 2. And then coefficients. We've got a 1, a negative 4, a negative 7, a 3, and a 6. And we leave our little separator down there for if we have a remainder. And then we bring down the 1 and we start multiplying. So 1 times 2 is 2. Add them together, -2. Multiply, -4. Add, -11. Multiply, -22. We doing this right so far? Let's see. Yeah, looks all right. 3 plus -22 would be -19. Times 2 would be -38. Plus 6 would be -32. And then this should be our remainder. And then we're going to have a constant term, a linear term, quadratic term, and a cubic term. So the answer should be x cubed minus 2x squared. Actually, you know what? I don't have enough room for that. Hang on. Let's start over to the left further. X cubed minus 2x squared minus 11x minus 19 plus -32 over the original thing we were dividing by, which is x minus 2. So remember with your remainder, it's whatever the remainder is over as a fraction, the original thing that was being divided. Now I'm just going to do a little bit of a double check here just to make sure everything went well, because those numbers got a little bit large. I'm just going to see what we get. Bear with me for just a second, because this will lead directly into today's lesson, which will be kind of a cool thing. Perfect. Cool. All right. So what we're going to be learning today, first of all, is called the remainder theorem. And then we're going to talk about something called the factor theorem. Now, the remainder theorem has to do with remainders. I mean, not really specifically one thing or another, but I do want to show you something real quick. If we plug in this value into the thing that we are dividing by, or the thing that is being divided, if we plug our value into this polynomial right here, take a look at what happens. What do you notice?
Same as the remainder.
Yeah. Plugging this value into this polynomial equals the value of the remainder, which is interesting. And that actually happens every single time in any function. So if you use synthetic division to evaluate for a particular value of x, the remainder ends up being that particular value of y on the function, which is kind of wild. Because the 2 was an x, the -32 is a y. So that means that if you were to find the equivalent function for this and graph it, you would have the point 2 -32 on that function. But you can also use synthetic division to get the exact same thing. That's the remainder theorem. I am not going to go into the details of this right here. It's sort of just like complex algebra jargon, which if you want to read through it and try to figure out what it's all talking about, that's fine. I'm not super interested in talking about the details here. What I do want to mention is at the bottom of this first page, because this is what we're going to be using a lot of today. So for any polynomial, p of x, so if you have some polynomial and some number a, which is going to be some x value, the remainder upon division by x minus a, which in this case would be like the one we just did, x minus 2, and then the a value would be 2. If you divide it and you solve for whatever a is, which in this case we were solving for 2, you can evaluate this particular function. So it says evaluate this function here when x is equal to 5. So you could plug in 5 for x. That's totally fine. 5 squared is 25. 4 times 5 is 20. So 25 minus 20 would be 5, and 5 plus 7 is 12. Now, that's pretty easy to use in mental math on something like this, but as it gets more complicated, sometimes synthetic division is actually quicker than trying to figure this out on your own or plugging it into a calculator. So with synthetic division, you would set this up here with your coefficients 1, -4, and 7 right here. And the value that goes up into the upper left-hand corner is just the number that you're evaluating for, which is 5. So here's our 5. So we drop down the 1, multiply, product goes here, add, you get 1, multiply again, 5, 7 plus 5 is 12. Same answer. So you can evaluate any point on any function using synthetic division. So direct substitution is that first one, square it, multiply it, combine like terms, get your number, or synthetic division, which I think is kind of cool. So you've got options now to figure out what you have on a graph. Now, if the remainder is 0, that just tells you that the y value happens to be 0, which also tells you an x-intercept. Like if you're trying to solve and you get a remainder of 0, that means that the y value is 0. So whatever x value it is, if your remainder is 0, is an x-intercept of a graph, which is a very important part of what we've been doing. So that might happen as well. So here we go. Applying the remainder theorem. So you can apply the remainder theorem to evaluate a function, and that's called synthetic substitution. You may find that synthetic substitution is a more convenient way to evaluate a polynomial function, especially when the degree of the function is greater than 2. Like I was saying, it can be actually a quicker process. For example, here, if you wanted to figure this out for an x value of -3, that might be a challenging thing to do, to just use mental math here to plug in -3 and try to figure out what's going on with that. So sometimes synthetic division might be a quicker method. So if we write it out, the value that we're going to be dropping up into our left-hand box here is going to be -3. So that's just going to drop in there. And then we have our coefficients. Why is there a 0 here? Why do we have a 0 as our second number? Yeah. Yeah, there's no exponent of 3 up here. No x to the power of 3, which means we need a placeholder, so 0. So we've got -2x to the 4th, and then 0x cubed, because there is no x cubed term here, plus 3x squared minus 15x plus 9. And then we're going to bring down the -2 and multiply. +6, 0 plus 6 is 6. Multiply again. 6 times -3 is -18. 3 plus -18 is -15. Multiply again. -15 times -3 is 45. -15 plus 45 is 30. 30 times -3 is -90. -90 plus 9 would be -81. So that means the remainder is -81. Therefore, if you evaluate the function with an x value of -3, you get a y value of -81. And then you can check it using direct substitution, which is exactly what I did with the warm-up, because I looked at that number. I was like, that's a -32. I want to make sure we did that right. So I plugged in 2 back into the original function on the calculator, and it worked out just fine. And this works out just fine as well. So because you have a nice method now for checking your answer, direct substitution, like you would normally figure it out, is now the check step, as opposed to being the only way to do it. So now you've got 2 ways to verify, which is always nice when you have 2 different ways of solving the same thing, because if you get the same answer in both methods, that means you're probably doing it correctly. So I'd like you to use synthetic substitution, synthetic division, for this one here. There are no missing coefficients on this one. And the number you're going to put into the upper left box is 8. So I'm going to give you a couple minutes to work through that. Figure out the corresponding y value, whatever the remainder is the y coordinate. I'll work on it as well. And you can do that in the margin on the left. There should be plenty of room for that. You got an answer? Yeah, what'd you get? What's that? I got a number that's not that big. Yeah. Anybody else? Julie? You got 9. Okay. Anybody else get 9? Yeah, I see some nodding. It is 9. Yeah. So let's see what happens here. So we got a -6, bring it down. -6 times 8 would be -48. Added to 52 would be +4 left over. 8 times 4 would be 32. Added to -27 would be a 5. 5 times 8 is 40. Added to -31 would be 9. So in that function, when x is 8, y is 9. Which, honestly, that took me a lot less time than it would have for me to actually try to figure out -6 times 8 cubed plus 52 times 8 squared minus 27 times 8 minus 31. That would be obnoxious to try to do by hand. Whereas this, you can evaluate this by hand real quick. So for me, it actually speeds up the process without a calculator. All right. Any questions on that one before we look at another couple examples of doing this, but this time with like context, putting a scenario around it? Today? Yes, we will. Yep. So we got like 2 more examples of this kind of thing, and then we're going to keep using synthetic division today, but we're going to do it to factor instead of just to figure out coordinates. So egg production, random. Okay, so the total production of eggs in billions in the United States can be modeled by that function, where x is the number of years since 2000. Predict the total production of eggs next year, apparently, 2025. So because we're talking about number of years since 2000, and we're going with the year 2025, that means our x value, the number we're evaluating for, is 25. So here's our 25, and then here's our function. Here's our cube coefficient, 0.007. Here's our quadratic coefficient of -0.149. Here's our linear coefficient, and then our constant coefficient is right there. So we'll drop down the 0.007. And if you multiply 0.007 by 25, you apparently get 0.175. And I'm just going to use a calculator. So we got -0.149 plus 0.175, and that gives us 0.026. And if you multiply that by 25, you end up with 0.65, which is right here, which are then going to add to 1.534. Yeah, right here. Julia. Oh, great. Okay. Sounds good. So we got 2.184 when we add those together. And then if we multiply that by 25, that should equal 54.6, which it does. Then we're going to go ahead and add that to the 84.755 for a remainder of 139.355. Good for that? Okay, that's a lot of eggs. That's 139.355 billion eggs. Yikes. Basically, we'd have to move the decimal 9 spaces to get the actual number. So it'd be 139,355,000,000 eggs. That's a lot of eggs. So next year, it's approximated that there will be that many eggs produced in the United States. I mean, if I think about it, I don't use eggs infrequently. I'll say that. Like, they're pretty common in my household. So
yeah, me too. We don't really like buy eggs.
Okay. Yeah.
Really good.
I don't have my own chickens. I kind of wish, because I know they're super fresh and like, yeah, and they probably save you a lot of money too. Yeah. Yeah, for sure. I do like eggs though. Fried eggs, especially fried eggs, they're delicious. All right. I want you to try this one. So it says the ideal weight of a kitten in pounds is modeled by that function, where X is the age of the kitten in weeks. So Determine the ideal weight of a 9-week-old kitten. So 9, that's going to be your X value that you're going to put in your upper left corner. So use the margin over here. So you're going to put your 9, and then there are no missing coefficients. So we got 0.009 followed by 0.127 followed by 0.377. Go ahead and go from there. Figure out the ideal weight. This is going to be in pounds. So however you write your answer, make sure you write it in pounds. You don't need to write pounds because that unit of measurement is already given. All right, what do we get? Yeah, 2.249 pounds. All right, so there's our answer, and then there's the work over there. What's up? Oh, no. Like of the new ones that we're using? Yeah. Mr. Lin would have them, and Miss Curtis would have them, but I don't think she's here today. So, yeah, you're welcome. All right, so here's the work over here. And then using synthetic division, we end up with 2.249. So after 9 weeks, you would expect the ideal weight of a kitten to be about 2.249 pounds. It's a very specific number. Kittens, I guess, are very small, even after 9 weeks. 2 pounds is not much. That's a great question. I'm sure somebody gathered lots of data over time and then threw it into a computer and then had that computer create a model, which then came out with that particular. Yeah, that would be my guess. That's usually like how things like that are done. It's people take in a lot of information over time. Like a computer does a lot of work, aggregates things, and then generally will show sort of a function of how the weights end up looking. So yeah. All right. So not only can you use synthetic division to figure out certain points on a function, you can also use synthetic division to factor, which we actually did previously back in Unit 3. That was the whole idea of synthetic division, was kind of to factor in the first place, to try to get things factored that might have been a little bit more challenging to factor. However, it works even better when you have more complicated things. And so when a binomial evenly divides a polynomial, the binomial factor, or the binomial is a factor of the polynomial. And down here, I'll give you an example. So we can also do other examples off to the side. But the quotient of this division is called a depressed polynomial. So whatever the answer is, the quotient would be the answer. And whatever that quotient is defined as a depressed polynomial. And that depressed polynomial has a degree that is 1 less than the original polynomial. And that's because you're factoring out a linear binomial. So if you factor out a linear binomial from this, that means you're factoring out 1 degree of x. And so if you factor out a degree of x from this, then there's the degree of x that got divided out right there, the linear binomial, which means that this has to be reduced by a factor of 1, which would then be a quadratic. So it goes from a cubic to a quadratic. So the depressed polynomial has a degree that is 1 less than the original polynomial. So it goes from a degree of 3. And then the answer to that, the quotient, when you divide by it, ends up dropping down to a degree of 2. A special case of the remainder theorem is called the factor theorem. So this is like a branch off of the remainder theorem because something is a factor of something else if the remainder is what? Anybody remember? Zero. Something is a factor of something else if the remainder is 0. 4 is a factor of 12 because 4 is divisible, or 12 is divisible by 4 with no left over, right? There's no remainder to that. If you have something like, let's say, x squared plus 7x plus 10, both x plus 5 and x plus 2 would be factors because if you were to divide x squared plus 7x plus 10 by either one of those, you would get the other answer because if you were to use synthetic division or anything else, there would be no remainder. And if something is a perfect factor of something else, that means it is factorable, which means that if you set this equal to 0, you end up with an x-intercept. And if you set that equal to 0, you end up with an x-intercept. Everything seems to tie back to x-intercepts. This particular quadratic would cross the x-axis at -5 and -2. That's what would end up happening. Now, this particular cubic function here looks like it's divisible by x minus 6. Which means that, or not x minus 6, by x plus 6, which means that x plus 6 is a factor, which means that -6 would be one of the x-intercepts of this original cubic function. Now, if this can continue to factor, then that means that anything else that is a real number factor of this would be more x-intercepts. And so if you can keep factoring something, then keep factoring something. So we're going to try out the factor theorem here. And it's going to give us some directions on what to do. Now, off to the side, it says some depressed polynomials might not be factorable. In that case, the only factors are the divisor and the depressed polynomial. Now, just because it might not be factorable doesn't mean that there aren't still more answers. It just means there aren't any more whole number factors that we can be talking about. So, starting with example 3. Show that x plus 8 is a factor of 2x cubed plus 15x squared minus 11x minus 24. Then find the remaining factors of the polynomial. So we're going to use synthetic division. So we're going to take the number that makes this equal to 0, -8. It goes up in the upper left-hand corner. Then we're going to write the coefficients, 2, 15, -11, and -24. If it's telling us to show that this is a factor, what does the remainder need to be? 0. Yeah. If something is a factor, if this binomial is a factor of this polynomial, the remainder must be 0. So that number, to show that it's a factor, this number here ends up needing to be 0. So if we drop down the 2, multiply by -8, we get -16. Plus 15 would be -1. -1 times -8 is +8. Plus -11 would be -3. -3 times -8 is +24. And -24 plus 24 is 0. Therefore, x plus 8 is a factor. So because the remainder of 0, x plus 8 is a factor of the polynomial by the factor theorem. So that means that 2x cubed plus 15x squared minus 11x minus 24 can be factored as, here we go, x plus 8 times 2x squared minus x minus 3. Where did this come from? 2x squared minus x minus 3. Came from here. Yeah, that's the answer to the synthetic division. The remainder was 0. The constant term is -3. There's the -3. The linear term is -1x, which is the same as -x. And then the quadratic term is 2x squared, which is right there. So that means that the depressed polynomial is equal to the answer to the quotient, which is 2x squared minus x minus 3. If you can keep factoring this depressed polynomial, which is a quadratic trinomial, then we should try to keep doing that. So let's head over here and see if it factors. So in order to try to factor this, we would need to use the slip and slide method for factoring. So we take 2 and multiply it by -3, which would give us x squared minus x minus 6. And then we would look for two numbers that would multiply to -6 and add to -1, which would be x minus 3 times x plus 2. And there's one more step with slip and slide. That's to divide by the original value of a, which in this case is 2. So we're going to divide -3 by 2. We'll divide 2 by 2 as well. -3 does not divide by 2. Therefore, we need to slide the 2 back in front of the x here, which would then give us 2x minus 3. 2 divided by 2 is 1, so the other one will just be x plus 1. So it's factorable, which means that the depressed polynomial can be factored into 2x minus 3 times x plus 1. So the entire polynomial here, 2x cubed plus 15x squared minus 11x minus 24, can factor to 3 different linear binomials: x plus 8, 2x minus 3, and x plus 1. Now, I do want to bring something up, just in case anybody was wondering. If you saw something like this last week with 4 terms, what method would we have to use that we learned last week? Or at least that we talked about last week from this table right here. Grouping. 4 or more terms mean factored by grouping. This does not factor by grouping. Because no matter how you group it, it doesn't end up working with factoring by grouping, which means there isn't really an option to factor like we used last week, which basically means the only option here would be to test values to see if you can use synthetic division to make it work, which you can. Now, it was nice that it told us that the factor was x plus 8, but if we didn't know the factor, we would just have to try a few things until we got it figured out. So let's turn the page. And in the spirit of trying some things to see if it works, take a look at this. Select all of the factors of 3x cubed plus 10x squared minus 27x minus 10. How in the world do we know if this is a factor or not? What do we have to use to find out if it's a factor? What have we been using all lesson? What's that? To synthetic division, right? Yeah. So we have to test this to see if it's actually a factor or not. So we have to test this using synthetic division. And then if the remainder is 0, that means it's a factor, which will actually make the rest of the problem simpler. But if this doesn't work, then we need to try the next one. And if that doesn't work, we need to try the next one. So let's start off by using, we're going to use -2 or 2 to start off with. 2. Okay, Zane? Yeah.
Could it be an amount of decimals, so like an infinite amount of decimals, like places, so you wouldn't be able to find the answer if it was like, well, it would take you an absurd amount of time to find one that only factor was like 0.0000.
So the only way it can be a factor is if you end up with a linear binomial with no decimals. That's the only way it's factorable. It doesn't mean there aren't any answers or solutions for when the graph crosses the x-axis, but in terms of it actually being factorable, it needs to be a whole number. Yeah. So that definitely simplifies that question a little bit, but there's nothing keeping an x-intercept from having an infinite amount of decimals. But in terms of something being factorable, it does have to be an integer value, which is kind of nice. So here we go. 2 in our corner, and then we're going to have a 3, a 10, a negative 27, and a negative 10. We don't have any missing coefficients here, so that's nice. So we're testing to see if x minus 2 is a factor by plugging in a 2 for x there. All right, if we get a remainder of 0, we know that's a factor, which means we can then keep working from there. So we'll bring the 3 down, and then 3 times 2 is 6. 6 plus 10 is 16. 16 times 2 is 32. Plus negative 27 would be 5. 5 times 2 is 10, and negative 10 plus 10 is 0. Hey, that's nice. So the first one we checked is a factor. That's excellent. Because what that means is we've got ourselves no remainder, which means that x minus 2 is a factor. We have a constant value of 5, a linear term of 16x, and a quadratic term of 3x squared. So that gives us x minus 2 times 3x squared plus 16x plus 5. So we know A is a solution here. Now the rest of it, we don't need to keep continuing to check using synthetic division. We can take this quadratic and try to factor it using slip and slide. So if you multiply 3 by 5, that'll be 15. So that'll give us x squared plus 16x plus 15. This is going to definitely be factorable, because two numbers that would multiply to 15 and add to 16 would be 15 and 1. So that would be x plus 15 times x plus 1. And then we divide both sets of parentheses, the numbers in them, by the original value of a, which in this case is 3. So divide by 3, divide by 3. 15 divides by 3, so that's going to be x plus 5. 1/3 doesn't divide, so we need to slide the 3 in front of the x, and that gives us 3x plus 1. So this will factor to x minus 2 times x plus 5 times 3x plus 1. So there's the work for the factoring down there. And then our answer, in terms of factoring, that's what it factors to. So A, B, and E. So those are the three solutions, A, B, and E. And it was fortunate that the first one we tried ended up being a factor, because that made the rest of it a little bit quicker. Last question. Let's talk about this one off to the side. Suppose you were asked to determine whether 3x plus 4 is a factor of that. Describe the steps necessary. So I mentioned earlier in class that not only do we have to divide by a linear binomial, but the coefficient of x needs to be 1. So, quick reminder. I'm going to go back to the bookmark there. Unit 3 real quick. Nope, Unit 4. Sorry, not Unit 3. Unit 4. There we go. So, right here. If you remember back to this is lesson 4 from Unit 4, synthetic division, or just dividing polynomials. If you're using synthetic division, and what you are dividing by it is linear binomial, but it does not have a coefficient of 1. You can get it a coefficient of 1 by dividing by the number with x. So this was a 2x minus 1. Everything in the equation got divided by 2 in order to basically reduce everything by a factor of 2. So we could do the same thing here. We would just have to divide both parts of this equation by what? Or both parts of this polynomial by 3 in order to make that work. So I'm just going to put an arrow right down there. Now let's just work on this one right here. So what we're looking at is, suppose you were asked to determine whether it's a factor. That means, so if 3x plus 4 is a factor of 3x cubed minus 2x squared minus 8x. Then 3x cubed minus 2x squared minus 8x divided by 3x plus 4 has a remainder of what? Something is a factor, the remainder has to be what? 0. Good. All right. So let's find out. If we're going to do this, that means that the entire numerator, everything on the numerator and everything on the denominator must first be divided by 3. So on the numerator, 3 divided by 3 is 1. That's great. So that's just going to be x cubed. Negative 2 divided by 3 would be negative 2/3 x squared. And then negative 8x divided by 3 would be minus 8/3 x. Because 8 doesn't divide by 3 evenly. On the denominator, 3 divided by 3 is 1, so that'll just be x. That's what we were going for. That's the whole reason we did this. And then 4 divided by 3 is 4/3, so plus 4/3. So if we're going to find out if this is a factor, we're going to use synthetic division with what fraction in our upper left-hand corner? What value of x makes the denominator 0? Negative 4/3, yeah. So negative 4/3. Good. So we got negative 4/3. And then the coefficients we're using are 1, negative 2/3, negative 8/3, and what goes at the end? There's no constant value, so what do we have to have at the end? Got to have 0. Okay. So here we go. 1, negative 2/3, negative 8/3, and 0. There it is. So you're going to bring down the 1. Multiply by negative 4/3. Well, that's negative 4/3. Now, in terms of addition, this is pretty convenient because negative 2/3 plus negative 4/3 is what? Yeah, negative 2. Negative 6/3, which equals negative 2. If we multiply negative 2 times negative 4/3, that would be equal to negative 8/3, right? Or 8/3 rather, positive 8/3, yeah. So 8/3, and take a look. What does that equal? 0. And actually, we didn't even need the 0 at the end. So we've got a remainder of 0. And coefficient of 0. Actually, that does need to be there. So that would be 0, and that would be 0 again. Sorry. There we go. 0 and 0 again. Keep the 0 here. 0 times anything is 0, 0 plus 0 is 0. So a remainder of 0, a constant of 0, a linear term of x, and a quadratic term of x squared. So this would factor to equal, let's see, we would have 3x plus 4 is a factor, and it multiplies by x squared minus 2x. What's that? Plus 0 if you want, but this actually factors as well because those both have a factor of x. So you can just divide an x out of both of those, which would end up being, I'm just going to put the x at the front, and then I'm going to write 3x plus 4. And then in the parentheses here, if you divide an x out of each of those, that would be x minus 2. Which means that the polynomial of 3x cubed minus 2x squared minus 8x should have 3 x-intercepts. One at 0, one at negative 4/3, and then one at positive 2. In fact, to wrap things up, let's see if that's true. So the equivalent function here would be 3x cubed, because it's always good to bring it back to the graphing side of things, because it's easy to kind of get caught up in the algebra and not remember what we're actually doing. And what we're actually doing here is figuring out x-intercepts. So this function here, if we look at our graph, should end up with x-intercepts at -4/3, 0, and +2. So let's find out. Let's get our calculation. Let's get a 0. I'm going to go to the left. And this first one should be -4/3, which would be -1 1/3, or about -1.3 repeating, and -1.3 repeating. The one in the middle looks like it's at 0. Let's just verify that. There it is. It's at 0. This one over here looks like it's at 2. Let's just verify that as well. And there it is at 2. So all that stuff that we're doing is still figuring out x-intercepts. And the earlier stuff we did in the lesson was using synthetic division to figure out coordinates on a function. So cool. All right. That's it for lesson 3. We only have one more lesson after this for this entire unit. It will take 2 days.